Hi, my name is Lauren White. In this lesson, we'll learn how to identify straight-chain alkanes. So we'll first discuss the definition of a straight-chain alkane. Then we'll talk about how to use that definition to identify whether or not a given molecule is a straight-chain alkane. Alkanes are just hydrocarbons in which the carbon-carbon bonds are all single bonds. As it turns out, alkanes can be found as straight-chain, branch-chain, or ring-shaped molecules. So how then can we be sure that a molecule is a straight-chain alkane? Well, in straight-chain alkanes, each carbon atom will be bound to only 2 or fewer carbon atoms. Remember that each carbon can only have 4 total bonds, and in straight-chain alkanes, 1 or 2 of those bonds will be to another carbon. So using the example of a straight-chain alkane we have here, we can count the number of carbon-carbon bonds on each carbon atom. So the first carbon here is bound to only 1 other carbon. The second carbon, though, is bound to the carbon before it and the carbon after it for a total of 2 bonds to other carbons. The third carbon, like the first one, is only bound to 1 other carbon. Since each carbon has 2 or fewer bonds to other carbons, this is a straight-chain alkane. So let's practice this together. We'll use our definition of straight-chain alkanes to identify which molecule in each pair is a straight-chain alkane. There are 2 ways you can do this, using the formula given or by drawing our Lewis structure. Since we're given a formula here for part A, let's practice that strategy first. The first carbon in this chain we can see is bound to 3 hydrogens, and the second carbon in the chain for a total of 1 bond to other carbons. Carbon 2 is bound to 2 hydrogens, the carbon before it, and the carbon after it for a total of 2 bonds to other carbons. Since this molecule is symmetrical, you can probably guess what the next 2 carbons will look like. Carbon 3, like carbon 2, is bound to 2 hydrogens, the carbon before it, and the carbon after it for a total of 2 bonds to other carbons. Finally, carbon 4 is bound to 3 hydrogens, and the carbon before it in the chain for a total of 1 bond to carbon, just like carbon 1 in this molecule. Now, since each carbon in this molecule is bound to only 1 or 2 other carbons, this is a straight-chain alkane. Let's look at the other molecule in this pair, though. The first carbon, like the other molecule, is bound to 3 hydrogens and the carbon that comes after it for a total of 1 bond to other carbons. Carbon 2, however, is only bound to 1 hydrogen, and this should get you thinking that something's a little different here. So carbon 2 is bound to the carbon before it, and then you see we have this parentheses with a subscript of 2. What this means is that carbon 2 is bound to 2 separate CH3, also called methyl, groups. So we can sketch this out, and we see in this molecule, carbon 2 is connected to 3 other carbons. Since we found a carbon that has more than 2 bonds to other carbons, this is not a straight-chain alkane. So let's try another example. Here, we're given the Lewis structure, so this is a great time to practice the other strategy of analyzing bonds that are drawn in the structure. So again, we want to look at how many carbons are bound to other carbons, but there are a lot of hydrogens here. Don't let this throw you off. The hydrogens don't matter in identifying whether or not the molecule is straight chain. A good way to handle these types of molecules is to pretend the hydrogens aren't there. So we're only really concerned with the carbons that form the backbone of this chain. Now I hope you've noticed something different about this chain. Since it's drawn out for us clearly with the Lewis diagram, we can see that there's a branch point in the middle of this molecule on carbon 4. This is in fact a branch chain alkane. But let's prove that it's not a straight chain alkane by looking at this carbon that kind of stands out. So looking at carbon 4, we can see it's bound to the carbon before it and the carbon after it, just like we're used to, but there's an extra carbon up top for a total of 3 bonds to other carbons. So this is a branch chain alkane, not a straight chain alkane. For the second molecule here, we can do the same thing. Ignore the hydrogens. We're only worried about the carbons that form the backbone. And notice there's no branch point here. There is a bend in the molecule on the far right, But we can always double check to make sure that that carbon is only connected to 2 other carbons. And in fact, it's bound to the carbon before it and the carbon after it for a total of 2. The molecule on the right is a straight chain alkane. So here's our last example. And notice our structure is still drawn out for us, but there are no hydrogens. So what happened to them? Well, they're still there, but it's common in organic chemistry to hide those hydrogens so they don't clutter up our structure. This is very similar to how we ignored the hydrogens in the last question we did. A good rule of thumb with structures drawn like this is that the ends and any corners are all going to be carbons. Let's start with carbon 1. Now remember, our hydrogens aren't explicitly drawn for us, but they are still there, and if it helps, you can draw them. So let's look at this molecule. Do you see any areas that look suspicious, like they might be a branch point? I don't. And in fact, when we look, all the carbons in this molecule are only connected to the carbons before and the carbons after them. So this is indeed a straight chain alkane. However, look at the second molecule. There is a branch point here. That should make you suspicious when you see it. Let's prove that it's not straight chain. If we look at how many carbons are connected to this carbon, it's connected to the carbon before it, the carbon after it, and that extra group up top for a total of 3. So the molecule on the right is not a straight chain alkane. The molecule on the left is a straight chain alkane. Now you should feel more comfortable identifying straight chain alkanes given a Lewis structure or a molecular formula.